Okay, part B, solving the differential equation. They're kind of quite routine, aren't they? So auxiliary equation, m squared plus 4m plus 5 equals 0, and that gives you that m equals minus 2 plus or minus I. And so the complementary function, and if you're like me, you'll just get really confused with all the names of everything, but that is x equals e to the minus 2t lots of a cos t plus b sine t even. And then we've also got this 8 sine t here, and so our particular integral, we can try using x equals lambda sine t plus mu cos t. Sometimes when your particular integral contains the right hand side, it doesn't like it, but it's okay for this one. I'll probably talk to you a bit more about that. It's slightly off spec, I think. But dx dt is equal to lambda cos t minus mu sine t. Second derivative. So differentiating again, minus lambda sine t minus mu cos t. The other thing I meant to say, if you don't like all these Greek letters, you could just call that one A and that one B. I quite like the Greek letters personally, and my B's look a bit like 6s. But, or, you know, any letters of your choice is fine. So this needs substituting into our original equation now, up here. So I can call that one. So substituting in. So we get minus lambda sine t minus mu cos t, 4 lots of dx dt, which is cos t minus 4 mu sine t, and then 5 lots of x plus 5 lambda sine t plus 5 mu cos t, and all of that is equal to 8 sine t. And so we're basically looking at equating coefficients of sine t and cos t. So if we start with sine of t, then I've got minus lambda cos sine minus 4 mu plus 5 lambda is equal to 8. That tidies up to give you lambda minus mu. So lambda minus mu equals 2, equation 1, and then equating coefficients of cos t, so I've got minus mu plus 4 lambda plus 5 mu. So it's just keeping your algebra tight. But actually your homework on this was really good. I was really pleased with that. And so that gives you lambda plus mu equals 0. Equation 2. And from there, lambda is equal to 1 and mu is equal to minus 1. So you can use your calculator, and that one you might even be able to just see it. And so substituting in, I'm going to write this on the next board, be clever about it. You end up with x equals e to the minus 2t, a cos t plus b sine t plus sine t minus cos t. So that's just adding on the particular integral to the complementary function. And we know that when t is 0, x is 5. So that gives you 5 is equal to a minus 1 from here. And so a is equal to 6. If a was equal to 0, I would definitely substitute it in, otherwise it's sort of marginal. I need to now differentiate this to get dx dt. So we've got product rule again, so it just kind of rears its head a little bit on these. So it's e to the minus 2t, lots of the bracket differentiated, which will give me b cos t minus a sine t. I've just swapped the order to make it look a little bit neater. And then I need to differentiate the e to the minus 2t, minus 2e to the minus 2t, and then not differentiate the bracket. So a cos t plus b sine t. And I'm differentiating this as well, so it's plus cos t, and minus cos t will go to plus sine t. So you sort of can expect a bit of product rule differentiation in here. I'm sure you've discovered that already. And we know that dx dt equals 2 when t is equal to 0. And so 2 is equal to b minus 12 from here, because a is equal to 6. And then plus 1 from here. So all the signs are going to 0, all the cosines are going to 1. And from there, b is equal to 13. So we do now have this full equation. So x is equal to e to the minus 2t, 6 cos t plus 13 sine t plus sine t minus cos t, and you're probably thinking, what has that got to do with simple harmonic motion? So part C of that question was describe the motion when t is large. So t large, we might as well let t approach infinity and just see what happens. So as t gets big, e to the minus 2t, which is 1 over e to the 2t, that's going to approach 0, and at quite a quick rate because it's an exponential function. And so all this bit is going to 0, and so x is approximately equal to sine t minus cos t, and then you can put that into your r sine of t minus alpha form, because we've got this minus here. And so that is equal to r sine t cos alpha minus r cos t sine alpha, and then you can match up your coefficients. So r cos alpha is 1, r sine alpha is also equal to 1. Right angle triangles, so this should all feel hopefully quite routine. Root 2 on the hypotenuse. And so I forgot what I'm doing. If I divide one by the other, you get tan alpha equals 1. So that's just dividing those. So sine over cos is 1, and alpha is equal to pi by 4. And so x is equal to root 2 sine of t minus pi by 4. So that is simple harmonic motion because it's a sine curve. So motion is simple harmonic motion. So if you're asked to describe and it's simple harmonic, you can just write that. With amplitude of, my pen's running out, that's quite fortuitous, with amplitude of root 2, and there's been no stretch on the x-axis for this one because we've got this t here, it's just been moved right pi by 4. So amplitude of root 2 and period 2 pi. So that's kind of going to town on describing that simple harmonic motion. I'm hoping you can read that, but I'm sure you can work that, so okay. So that's a case of forced harmonic motion. So the system's been forced into harmonic motion, and it's oscillating without decay, so the amplitude is remaining constant, and those oscillations are just going on forever.